Understanding the observable universe versus the entire universe. Look up at the night sky. Every star you see, every galaxy visible through our most powerful telescopes, every distant quasar shining from billions of light years away, all of it, everything we've ever observed or could theoretically observe, is contained within what astronomers call the observable universe. But here's the profound question: is that all there is? Or does the universe extend far beyond what we can see, perhaps infinitely in all directions? This distinction between the observable universe and the entire universe is one of the most important concepts in cosmology, yet it's often misunderstood or overlooked. Today, we're exploring what these terms really mean, why there's a difference between them, how we know the observable universe has a definite size while the total universe's size remains unknown, and what this tells us about the fundamental nature of reality itself. This isn't just academic philosophy, it has real implications for what we can know about the cosmos and what must forever remain beyond our grasp. Defining the observable universe. Let's start with the observable universe. What exactly does this term mean? The observable universe is the spherical region of space from which light has had time to reach us since the beginning of the universe. It's centered on Earth, or more precisely, on any observer, and it has a definite, measurable size. The key limiting factor is the finite age of the universe combined with the finite speed of light. The universe is approximately 13.8 billion years old. Light travels at 300,000 kilometers per second, but it's been traveling through expanding space. Taking cosmic expansion into account, the most distant observable objects are now about 46 billion light-years away. This means the observable universe is approximately 93 billion light-years in diameter, a sphere with a radius of about 46 billion light-years in every direction from Earth. But here's something crucial to understand. The edge of the observable universe is not a physical boundary. There's no wall, no barrier, no place where space ends. The edge is purely observational. It's the limit of how far light has had time to travel to reach us. Think of it this way. Imagine you're standing in a vast, dense fog. You can see clearly for perhaps 50 meters in any direction, but beyond that, the fog obscures everything. That 50-meter radius doesn't represent the edge of the world, it's just the edge of what you can see. The world extends far beyond your visible range, hidden by the fog. The observable universe is similar, except instead of fog limiting our view, it's the finite speed of light combined with the finite age of the universe. Light from regions more than 46 billion light-years away simply hasn't had time to reach us yet. This has a surprising implication. The observable universe is growing, not because the universe itself is growing, though it is expanding, but because more light is reaching us from previously invisible regions. Every second we can theoretically see a bit farther as light from more distant regions arrives. It's also important to note that the observable universe is different for different observers. An alien astronomer in a galaxy 10 billion light-years from us would have their own observable universe, a sphere centered on them. Their observable universe would overlap with ours significantly, but each would contain regions the other cannot see. There's no privileged position in the universe. Every point sees itself at the center of its own observable universe. We're not at the center of anything special. We're just at the center of what we can observe, as is every other observer in the cosmos. The particle horizon. The boundary of the observable universe is technically called the particle horizon. This is the farthest distance from which matter and its emitted light haven't had time to reach us since the Big Bang. To understand this precisely, we need to think about light's journey through expanding space. When we say the universe is 13.8 billion years old and light travels at a fixed speed, you might think the observable universe should be 13.8 billion light-years in radius. But cosmic expansion changes this calculation. In the early universe, space was denser and expansion was faster.
As a photon traveled toward what would eventually become Earth, that galaxy was much closer to us then, perhaps only 1 billion light-years away, due to the universe being smaller. But during the 13.4 billion years it took the photon to reach us, space expanded dramatically. That galaxy is now about 46 billion light-years away. The particle horizon calculation requires integrating the expansion history of the universe, accounting for how the expansion rate has changed over time due to matter density in the early universe and dark energy dominance in the late universe. The result is that the particle horizon is at about 46 billion light-years, making the observable universe about 93 billion light-years across. But this horizon is not absolute. It shifts based on what we're measuring. The particle horizon represents the farthest distance from which matter could have traveled to reach us. There's also the light horizon, the farthest distance from which light could have traveled, which is essentially the same in our current universe. More subtly, there's the cosmological event horizon, which represents the farthest distance that we could ever send a signal that would reach a distant observer. Due to accelerating expansion driven by dark energy, there are regions of space that are moving away from us so quickly that light emitted from Earth today will never reach them, even given infinite time. The event horizon is currently at about 16 billion light-years. These different horizons illustrate that observable depends on what you mean. The particle horizon defines what we can currently observe. The event horizon defines what we could ever influence or receive signals from in the future. What lies beyond the observable universe? Now, the profound question: what exists beyond our observable universe? The honest answer is we don't know for certain, and we may never be able to know through direct observation. By definition, anything beyond our particle horizon is causally disconnected from us. We cannot receive signals from there, and we cannot send signals there. But we can make educated inferences based on physics and observations. The most straightforward possibility is that the universe simply continues beyond what we can see. The same laws of physics apply. More galaxies, more stars, more cosmic structure, just like what we observe, but forever beyond our view. This is called a homogeneous and asymmetric universe, and it's the simplest assumption consistent with observations. Evidence supports this view. When we look in any direction, the observable universe appears statistically similar. The density of galaxies, the distribution of matter, the patterns in the cosmic microwave background, all are uniform on large scales. This uniformity suggests that there's nothing special about our observable region. It's just one patch of a much larger, possibly infinite universe. Cosmic inflation theory provides additional support. Inflation suggests that in the first fraction of a second after the Big Bang, the universe underwent exponential expansion, growing by at least 10 to the 26 times in an incredibly brief time. If inflation is correct, the entire universe, far beyond what we can observe, was inflated together from a tiny quantum region.
Inflation predicts that the total universe should be vastly larger than the observable universe. Some estimates suggest the total universe could be at least 10 to the 23 times larger than what we can see, a number so vast it's effectively infinite for all practical purposes. If inflation lasted even slightly longer than the minimum required, the universe could easily be infinite in extent. But could the universe be finite? Yes, if it has an unusual topology. The universe could loop back on itself like a three-dimensional version of a torus or hypersphere. Imagine a video game where moving off the right edge of the screen makes you appear on the left. The universe could have similar wraparound properties in 3 dimensions. Current observations constrain this. If the universe were finite with such topology and small enough, we'd see repeated patterns, the same galaxies or structures appearing multiple times in different directions. We don't observe this, suggesting that if the universe is finite, it's much larger than the observable universe. The simplest interpretation of current data is that the universe is either infinite or so large that the difference doesn't matter observationally. But we cannot rule out finite topologies that are much larger than what we can observe. The cosmic microwave background as a limit.
There's another important limit to what we can observe, distinct from the particle horizon, the cosmic microwave background itself. The CMB represents the surface of last scattering, the moment when the universe became transparent to light, about 380,000 years after the Big Bang. Before this, the universe was opaque, a plasma where photons constantly scattered off free electrons. We cannot see through this barrier with electromagnetic radiation. The CMB is located at about 46 billion light-years away in every direction. It defines the edge of our observable universe for electromagnetic observations. Beyond the CMB, earlier in time, we cannot see using light. However, the universe didn't become transparent to other particles at the same time. Neutrinos decoupled from matter when the universe was just 1 second old. Gravitational waves have traveled freely since even earlier, potentially from the very first moments of the Big Bang. This means that while the CMB is the limit for optical and infrared observations, there could theoretically be a cosmic neutrino background that would let us observe the universe at 1 second old, and a cosmic gravitational wave background that might reveal the universe at even earlier times. Future detectors might observe these signals, extending our observational reach closer to the Big Bang itself. But they wouldn't extend our reach farther in space, they'd extend it earlier in time. The spatial limit defined by the particle horizon remains, set by the speed of light and the age of the universe. Infinity and the universe. One of the mind-bending aspects of this discussion is the possibility that the universe is infinite. If the universe is infinite, it always has been infinite. The Big Bang didn't happen at a point that then expanded into empty space. Instead, the Big Bang happened everywhere simultaneously. An infinite universe was smaller and denser in the past, but still infinite in extent. Think of infinity being scaled up. If you have an infinite line and double the distance between every point, you still have an infinite line, just a stretched one. That's analogous to how an infinite universe expands. Every region of space expands, but space extends infinitely in all directions at all times. This has strange implications. In an infinite universe, everything that can happen does happen, somewhere. Not just once, but infinitely many times. There would be infinitely many Earth-like planets, infinitely many observers identical to you. Every possible arrangement of matter permitted by physics exists somewhere. This isn't science fiction or speculation. It's a mathematical consequence of infinity combined with finite possibilities. If you have infinite space and only finite ways to arrange matter, which quantum mechanics suggests, then every arrangement must repeat infinitely often. However, these duplicates would be staggeringly far away, distances requiring not just billions or trillions of light years, but numbers so large they require exponential notation to express. You'd never encounter or communicate with these alternate versions. They're beyond any practical horizon, forever inaccessible. Some physicists find the infinity concept troubling. It leads to unusual questions about probability and counting. If infinitely many observers exist, how do we assign probabilities to observations? This problem has led to sophisticated philosophical debates in cosmology. Others embrace infinity as the simplest possibility consistent with observations. It requires no special boundaries or edge conditions. It treats all space democratically. No location is special. Whether the universe is finite or infinite remains an open question. Current observations are consistent with infinite extent, but cannot prove it. The universe could be finite, but so large that it appears flat and infinite within our observable region. Multiverse considerations. The discussion of observable versus the rest of our universe is not a multiverse in the sense often portrayed in science fiction. It's all one universe with the same physical laws, just extending beyond what we can observe. However, some theories do propose actual multiverses, separate regions of reality with potentially different physical laws or properties. Eternal inflation, for example, suggests that while inflation ended in our region of space, it continues in other regions, creating bubble universes causally disconnected from ours. These bubble universes would be fundamentally different from the unobservable parts of our universe. They might have different values for physical constants, different particles, or even different dimensions of space. They would be completely separate realities.
These ideas are highly speculative and may be untestable by their very nature. If other universes are causally disconnected, if no signal could ever pass between them and us, can they be considered part of science? This is an active philosophical debate. The key distinction is this: the unobservable parts of our universe beyond our particle horizon are extensions of what we can see with the same physics. Proposed multiverse scenarios involve separate regions with potentially different physics. The former is a straightforward consequence of finite light speed and cosmic age. The latter is speculative theoretical physics. What we can and cannot know. This discussion highlights fundamental limits on knowledge. Some questions about the universe may be unanswerable not due to technological limitations, but due to the nature of causality and observation. We can measure the observable universe precisely. We know its size, age, composition, and evolution with increasing precision. We can test theories against observations, make predictions, and refine our understanding. But we cannot measure the total universe if it extends beyond our particle horizon. We cannot observe what happened before the CMB became transparent with electromagnetic radiation. We cannot send signals to regions beyond our event horizon or receive signals from beyond our particle horizon. These aren't temporary limitations waiting for better technology. They're fundamental constraints imposed by the speed of light, cosmic expansion, and the age of the universe. This might seem frustrating. Surely complete knowledge should be possible in principle, even if not in practice. But the universe is under no obligation to make itself fully comprehensible to observers within it. Some truths may be fundamentally inaccessible. However, we can make inferences. We can use physics, which we test and verify within our observable region, to reason about what likely exists beyond our horizon. If the laws of physics are universal, then the universe beyond our view probably resembles what we can see. This is analogous to how we reason about history. We can't directly observe the past, but we can infer what happened based on evidence and physical laws. Similarly, we can infer properties of the unobservable universe based on observations and theory within the observable region. Practical implications. Does this distinction between observable and total universe matter practically? For most astronomy and astrophysics, focusing on the observable universe is sufficient. When we study galaxy formation, stellar evolution, or cosmic structure, we're working within our observable region where we have data. But the distinction matters for cosmology and fundamental physics. Understanding cosmic expansion, testing inflation theory, measuring global geometry, and probing the nature of space itself require understanding these observational limits. It also matters for how we think about humanity's place in the cosmos. If the observable universe is all that exists, then we can, in principle, catalog everything. The universe is vast but finite in content. But if the universe extends infinitely beyond what we can see, then we're truly insignificant in scale. Not just one planet among billions in our galaxy, not just one galaxy among trillions in the observable universe, but one observable region in an infinite cosmos. No matter how much we discover, infinitely more lies beyond our grasp. This perspective can be humbling or inspiring. We're part of something vastly larger than we can observe or influence. Yet we can still study, understand, and appreciate the portion of reality accessible to us. Future observations. Will we ever extend our observational reach significantly beyond current limits? In terms of electromagnetic observation, the CMB represents a firm barrier. We cannot see earlier with light because the universe was opaque before recombination. However, gravitational wave astronomy might eventually detect the cosmic gravitational wave background, produced in the very moments after the Big Bang or during inflation itself. This would extend our observational reach to the very earliest times. Neutrino astronomy could potentially detect the cosmic neutrino background from when the universe was 1 second old. These observations would probe earlier times, but wouldn't extend our spatial reach beyond the current particle horizon. As time passes, the observable universe grows as light from more distant regions reaches us, but cosmic acceleration complicates this. Regions that are currently beyond our particle horizon and receding faster than light will remain forever inaccessible.
The event horizon ensures that parts of the universe will never enter our observable region, no matter how long we wait. In fact, due to dark energy-driven acceleration, the observable universe in the far future will contain fewer galaxies than it does today. Galaxies currently within our observable universe will accelerate beyond our event horizon and disappear from view. Future astronomers in 100 billion years might see a universe containing only their local galaxy group, with all other galaxies having receded beyond observability. Closing. So what's the difference between the observable universe and the entire universe? The observable universe is the region we can see, a sphere about 93 billion light-years in diameter, centered on Earth, defined by how far light has traveled to reach us since the Big Bang. It has a definite, measurable size. We can map it, study it, and understand its contents and evolution. But the entire universe is everything that exists, all of space, everywhere. It might be infinite, extending forever beyond our observable region, or it might be finite but vastly larger than what we can observe. We can't measure it directly because we're limited by the speed of light and the age of the universe. The distinction matters because it defines the boundary between what we can know through observation and what we must infer through theory. It reminds us that the universe we observe is just one region of potentially infinite reality. But it's an extraordinary region to inhabit. In this observable bubble, we find 2 trillion galaxies, hundreds of billions of trillions of stars, and cosmic structure stretching across billions of light-years. We find evidence of cosmic inflation, dark matter, dark energy, and the Big Bang itself. From one small planet, using instruments built by human ingenuity, we've mapped the observable cosmos and uncovered its secrets. We've measured cosmic distances and ages. We've understood how galaxies form and evolve. We've peered back to within 380,000 years of the universe's beginning. That we can't see everything doesn't diminish what we have seen. The observable universe is magnificent in its own right, a vast laboratory where we can test theories, make discoveries, and deepen our understanding of reality. Thank you for exploring these cosmic boundaries with me. If you found this valuable, subscribe for more deep dives into cosmology and the nature of the universe. And leave a comment. Does the possibility of an infinite universe beyond our observation inspire or humble you? Keep wondering, keep questioning, and keep exploring the cosmos, both the parts we can see and the parts we can only imagine.